Mr. Hefner here, and here's a short video on force fields with parallel plates. So here's some parallel plates, just two metal plates connected to some potential difference, like a battery, and there we go. Okay. So parallel plates are simple tools. It's just two metal plates, like two pipe ends, for example, connected to a potential source, like a car battery, and you can use that if you cut a couple holes like this as a particle accelerator. If you try to shoot the electron or proton through the middle of them like this, it's a particle deflector. And if you add a magnetic field, it's a velocity selector. Three different things. Now this would be a do-it-yourself particle accelerator. Please don't do this. If you do this, you probably almost certainly will electrocute yourself. It's very dangerous. Okay. But I just did this as an example of what it would look like. Like anyone can make one. So here we got our homemade particle accelerator. Super dangerous. Don't do it. Okay. These plates are 20 centimeters apart and connected to a car battery of 12 volts. And we just get a CRT from an old television, and this cathode ray tube can shoot electrons into the plates for us. And in doing so, we can accelerate them. So let's say the electrons come in pretty slowly, like 0 meters per second. What is the exit velocity going to be? So if you take this and put it as a diagram, it looks like this. You've got a hole in a plate, The field lines show what a proton would like to do. In this case, the electrons will do the opposite. It's going to come in slow or zero, accelerate like crazy, and then come flying out. Okay. So a force solution or an energy solution is possible. Let's do the force solution first. So we get F equals ma, so here's our ma. The electric force is Q times the field strength, epsilon or E. And epsilon is just your voltage divided by your plate difference, so delta V over D. And so the charge Q is one elementary charge, which is 1.6 times 10 to the negative 19 coulombs. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. We have our 12 volts, we have our 20 centimeters, or 0.20 meters. And we get a crazy acceleration of 1.053 times 10 to the 13 meters per second squared. So that is a lot. That's 10.53 tera meters per second squared, because tera is 10 to the 12. Or if you divide by 9.8, which is one regular G value, that's 1.08 trillion Gs. So that's one heck of a G force there. So the particle accelerator, keep going. We just got to find the final velocity. If we come in at negligible or zero speed, okay, then the VI is just going to be 0 squared. We got 2 times the acceleration we found, times the distance, which is still 0.2 meters. And the electron will come flying out at just over 2 million meters per second, or 0.68% of the speed of light. So not fast enough to worry about relativity yet. A CRT, cathode ray tube, is also known as an electron gun, and basically just shoots electrons for you, like in the old TVs. Okay, so now we can do the energy solution. For the energy solution, I just like to use the law of conservation of energy. The electrical energy that goes in will be equal to the kinetic energy that comes out, and we'll assume the heat loss is negligible or zero. So the electrical potential energy is real easy to calculate. It's the charge Q times the potential difference, or voltage, delta big V. And kinetic energy, of course, is just mv squared over 2. This is final, so I'm using prime. Some people like to use a little subscript f instead. It's up to you. So v prime, my final velocity, is going to be to the square root of 2 times the charge times the voltage over the mass. Plug in our numbers here. The charge is one elementary charge, 1.6 times 10 to the negative 19 coulombs. The mass, 9.11, 10 to the negative 31 kilograms. And we got our 2 and our 12 volts. And we get the same answer. Just over 2 million meters per second. So which solution do you like better? Do you like force with acceleration and kinematics? Or do you like an energy solution? My personal preference is energy, but they're both good solutions. So now we're going to look at a particle deflector. This is used to deflect an ion. Old TVs, CRT televisions, they had one horizontal and one vertical, so that the electrons could hit different parts of the phosphorus screen. And oscilloscopes still use them. So here's an old TV here. At the very back there's the electron gun plus a couple parallel plates. And oscilloscope still uses the same technology to study waves, same thing. So we got two electrons. We got a slow one at 10 to the 4 meters per second. We got a fast one, 10 to the 6. So this has been set up so that the red one will impact the plates and the purple one will exit and be deflected but come out, okay, at a different velocity. So the plates are 6 centimeters apart with only 10 volts, and they're 4 meters long, which means halfway in the middle is 3 centimeters. So first thing we're going to do is find out if they impact or not by checking to find out the time it takes to exit versus the time to impact. Then we'll know which one wins. So the time to exit, first of all, so we got to travel 4 centimeters, 0.04 meters. Electron 1 is at 10 to the 4 meters per second. And so that's going to take, if you turn it into nanoseconds, 4,000 nanoseconds to get out of the plates. This electron is 100 times faster, and it turns out to be 40 nanoseconds to escape the plates. Okay. So now we have to find out how long it takes to hit the plate. So they both experience the same acceleration. So the electrical force QE, or QV over D, is going to cause the mass times the acceleration. So the vertical acceleration will be Q times the voltage divided by the mass and then the plate distance. And both of them are going to accelerate upwards at 2.927 times 10 to the 13 meters per second squared. It's a lot of acceleration. So now, how long does it take to crash if it crashes? They're both the same. Take the same amount of time to crash if they crashed. So we're going to have our distance up, which is 3 centimeters, or take the plate distance 6 divided by 2 for that. Okay. The initial speed up is 0 because they come in horizontal. Okay, moving forward. We have the acceleration, just found it, and the time squared to crash divided by 2. Rearrange it. The time to crash is the plate distance, which is 6 centimeters, divided by the acceleration. And it turns out to be 45.27 nanoseconds. So you can see the first electron, it needed 4,000 to escape, so it will impact at 45.27. This one escaped after just 40, so it's not going to impact, and it will not accelerate for the full 45.27, only for 40 nanoseconds. Okay, so in the X direction, there is no X electric force. Just like in projectile motion, there is no X force, but there's only a Y force, gravity. So there's only a force in one of the two component directions. So in this case here, in the X direction, I got the numbers here backwards. Okay, fix that. So yeah, V1, the first electron is moving forward at 10 to the 4 the entire time, and the second electron at 10 to the 6 forward the entire time. And then if it exits or crashes, I'm going to take the time. So the time for the electron 1 to crash is the 45.27 nanoseconds. And it was accelerating at that crazy acceleration. It's going to impact at 1,325,100 meters per second up while moving forward at 10 to the 4. The second electron is going to escape at 40 nanoseconds with the same acceleration. And when it leaves, it'll be moving upwards at 1.1 million, 1.17 million meters per second. Okay. So notice it took less time to get out than it did to impact for the other one. So to find out the final velocity, it's pretty easy. We're just going to use our vector components. So the Vf squared is equal to the Vfy squared plus the Vfx squared. So we're going to use Pythagorean theorem. And we're going to use tan, opposite over adjacent. So the y component divided by the fx component, shift tan. And when you plug in our numbers from up here, you get the first electron. So the first electron will impact at an angle of 89.7 degrees, so it's almost perpendicular. It's almost a direct collision at just over 1.3 million meters per second. the second electron will escape. It'll exit at a 49.5 degree angle and at just over 1.5 million meters per second. Okay, now velocity selector. So how do physicists know exactly how fast a particle is moving before it strikes a target? The particles are way too fast to see, right? So how do they know? So what they do is they combine electric and magnetic force fields. So using the third right-hand rule, or using Fleming's left-hand rule, you can find the force, the magnetic force acting on a proton or an electron, in this case a proton. So the proton is moving in. We got force field lines from north to south for the magnetic force. And if you use Fleming's law or the third right-hand rule, you'll find the proton will experience a force to the right. Okay. Meantime, while it's traveling through these plates, these positive-negative plates will make it want to go to the left. So all we need is for the magnetic force and the electric force to cancel each other out, and then we'll know exactly how fast the proton is, because the magnetic force depends on the proton's speed. So this is how you make a velocity selector. You get two metal plates connected to a battery or some kind of potential difference. You get two electromagnets or two giant bar magnets like this, okay, with a nice uniform magnetic force field. And boom, there you go. You got your velocity selector. So I'm going to take that this picture here. I'm going to rotate it a little bit, and this is what it would look like from a different point of view. So the force field, which was going up here, is now going to be coming out. So I got O's to show the force field coming out for the magnetic force field. Negative to positive here. The electric force field, which was coming out here, now it's going to be going up. So from positive to negative like this. And the proton's going to come in. Okay. All right. So we just need to use F equals ma. We want the acceleration to be 0 in the y direction because we do not want any deflection. So we need the magnetic force subtracting the electric force to add up to 0. And the magnetic force is QV cross B. And the electric force is QV over D. Okay, so we got little v for speed velocity, and we got big V for voltage here. And when we rearrange this, to find the voltage you would need, given the speed and the magnetic field and the distance between the plates. If we want a proton moving at 90% the speed of light inside a MRI type machine, or 3 Tesla, with 1 centimeter separation between the plates, then you would need a voltage, huge one, 8.1 million volts. It's a lot of volts, so probably not the best design here, but there you go. Notice that this equation only uses voltage, speed, magnetic field, and distance. So what's cool about this is the charge, Q and Q, canceled out. The mass times 0 didn't matter. So once you design a particle velocity selector, it works for all the particles. Doesn't matter what the mass, doesn't matter what the charge. It can be positive, negative, it doesn't matter. It's going to get through the same. So you can use this same selector for electrons, protons, alpha particles, any particle you want. If you want it moving at 90% the speed of light and you want to know for sure that it's doing that, you will know, and it'll hit your target. Okay. Here's another example. So let's say we need to find the magnetic field. Instead, we got an electron moving at 100,000 meters per second inside 120 volt plates. What are we going to do? So same thing. The charges cancel out. Mass times 0, it's gone. So the magnetic field, if you rearrange the equation from last time, it's just the voltage divided by the distance between the plates times the speed. And so in this case here, we would only need 0.12 Tesla of, or 1.2 centitesla of magnetic field strength, which is a lot more than the Earth's magnetic field of 45 microtesla or 0.545 millitesla. Pretty small. So in summary, there are 3 main uses for parallel plates. We use them for particle accelerators, like this situation right here, and also inside the old TVs right here, there's a particle accelerator. We use them as deflectors, like here in the old TV. We've got the horizontal and vertical plates. And we also use them as a velocity selector. You take the parallel plates with a magnetic field and you can select which velocity will go undeflected. There are plates do have one other use sometimes. They are used in rail guns, electromagnetic guns, which use a Lorentz force. So for example, this is the testing gun for the US Navy. And here's an example of how it works. So you put the projectile or the bullet on the two rails, and you also have to connect it to a potential difference. I see that's missing though, and they will boom cause it to accelerate on the two parallel plates or rails. Okay, there you go. I hope this helps.